Okay, well, good morning, guys. Good morning, everyone. Just to repeat what I said a bit before, I already have the exams graded. I just want to take a look at them one more time in order to see if I make some small adjustments. I went over very quickly through the exams, and I saw grades all the way from 64 to 93, I guess. So probably I will be posting the grades today, all right? All right, so just in terms of organization of the course, I want to let you know that we're getting into a point that we're about to finish with all the theory that we need in order to solve application problems. So probably you may find that part a little bit more interesting. Now it was a lot of new stuff, but you will see that now we'll get into more application problems, and probably that's going to be a little bit more of fun. Although I like the both parts. In order to finish that part, we still need to review a few things before we move on. If I'm going to ask you to come back in your notes, I asked you some time to leave some space free. Right before talking about failure of rocks, we had just finished about talking linear elasticity, right? And if you remember, we said that in order to find a general solution for any elasticity problem with some arbitrary boundary conditions, not just a simple fracture, a simple wellbore, we need to solve this equation over here. And that equation over here and many of the solutions that we're going to be using assume linear elasticity of isotropic media. So elastic means that there are always recoverable deformations. Linear means that there is a linear relationship between stress and strain. Isotropic means that the properties are the same in all directions. And also that implies that there is no plastic strain. But with rocks, that's not true, okay? We don't have the time to go through all of that theory to make more realistic rock models, but you should know that that's something which is out there, and if you want to expand a little bit your knowledge in geomechanics, that's probably something that you should definitely do in order to have more realistic Earth models. So the first thing that we're going to see is something which is called anisotropy. So anisotropy is the opposite of isotropy. It means that the properties vary according to the direction in which you measure them. With sedimentary rocks, usually you have layers. Why layers? Because all the grains and sometimes when you have evaporation, gets deposited thanks to gravity, and that forms horizontal layers. Those layers later, they may change in directions, they may break with faults, as we're going to see later, but mostly in sedimentary rocks, we're going to have horizontal layers. And it happens that rocks tend to be stiffer in the horizontal direction than in the vertical direction. So for example, if I were to take what is called a vertical plug or a vertical sample out of a sedimentary rock made out of layers, and I were to compare it with a horizontal rock sample, you will find out that for the same rock formation, you will find that the Young modulus in horizontal direction, this is the horizontal sample, is stiffer than the sample in the vertical direction. So this one is going to be EV, this is going to be EH, and usually EH, Young modulus, is higher than the modulus measured in vertical direction. So that's called anisotropy. And for some rocks, they are even more complicated. They have another plane of symmetry. If you have fractures in the rock, probably imagine that now you have fractures in the plane of the board. Then you will have another modulus, another stiffness in this direction. So it gets a little more complicated. A few days ago, a colleague of mine sent me a paper of a presentation in SPE of somebody that had titled a talk that was something like assuming isotropy in shales, a fatal assumption. So it was very, very strong, right? And with shales, it happens that they tend to be very anisotropic. Usually, the more clay shales have, the more anisotropic they are. So remember, and we're going to touch this in a little bit too. Here, I'm referring to the Young modulus, to the stiffness. Rocks usually have a different stiffness depending on the direction in which you measure. Second is something called elasto-plasticity. So what is elasto-plasticity? Elasto, as you may guess, comes from elastic. It means recoverable deformations. And plastic, it means permanent. Permanent deformations which are non-recoverable. If we wanted to put this in a simple example, if you were to load a piece of rock as you have done in the laboratory with an axial stress, and here I forgot to put that this was stress and strain. We can do something very similar. If this is strain and this is stress, you could load this rock. And do you remember when you did the unloading, that the unloading didn't follow the same slope of the loading process? Usually the unloading process is a little bit steeper. So this one is going up, this one is going down, and this one is loading, this one is unloading. And if you were to reload again, it will follow more or less the same path and continue on the loading path. Why do we have this unloading different than the loading? Any idea, any suggestion why we may have that? So imagine if we were to come back all the way, now I just came back a little bit, but if we were to come back all the way to here you will end up with a non-recoverable deformation. That means it's something that was permanently deformed. When we assume that something is elastic, that means that it's coming back always to the same size. But in this case, it's not coming to the same size, to the same dimension. And that's because we have some permanent deformations, it's some micro failure in the rock that usually we can't see, but it is there, something we cannot recover. And for example, here you could think of, say that we had a sandstone or just a sand. It's usually more evident with sand that when you load it, you make some of these grains to move a little bit against the others and have a little bit of friction. So that little bit of displacement after you load it is not going to be recovered because that's a shear displacement, and here if you have a small slip, it won't be recovered. And if it's not recovered, it's not going to show up over here. So usually this unloading modulus is higher than the loading modulus. And furthermore, you could load this sample even more until you get to the shear yield, and at that point the rock is going to reach more or less a peak or a plateau, depending if we are in triaxial conditions or not. I'll talk a little bit more about that later on. And here, if you do an unloading, also it will look something like this. And if you reload, probably it will go a little bit more and then may fall down. Here at this point, all of those are non-recoverable strains. And usually when we deal with rocks, we get many times to this point of non-recoverable strains. So when you get there, you need to, you cannot use linear elasticity anymore, because if you use that, say if you get to this very large strain, you will assume that if you were to follow linear elasticity, you will have a very high stress somewhere over here, but actually the rock has gone into failure, and you will never reach to that one. So you have to be careful. You need to know linear elasticity sometimes works well, some other times it doesn't, but you need to know when it does not work that well. And that's what we call elasto-plasticity, when we have plastic deformations that cannot be recovered. And the last thing I'd like to talk with you is a phenomenon of visco-elasticity. Real rocks have these three properties and sometimes some other things. They are anisotropic, they develop plastic strains, and they also develop viscoelastic strains. Where does visco comes from? From viscosity, right? So now we're adding to elasticity a viscosity term. And what is the law of viscosity that you saw in fluids? Do you remember that? The basic law of Newtonian fluids. If you remember that, that tells that the shear rate is proportional to the viscosity of the fluid and proportional to the shear strain rate. That's the law for a Newtonian fluid. That means that now that point over there means a derivative in time, right? So it means that the shear stresses are proportional to the velocity of strain. So now time is involved. This is a time-dependent phenomenon. For viscoelasticity, we're going to see that there are three basic ways in which we can observe viscoelastic response. So the first one is this one, depending on velocity of strain. So if I were to run the same test that I ran over there with strain here in the x-axis and stress in the y-axis, it wouldn't be the same if you load the rock in 1 second or if you load it in 1 year. It's not the same. So if you load it in 1 second, the same rock, your Young modulus is going to appear faster than if you load it in 1 year. So the Young modulus fast is going to be higher than the Young modulus slow. An everyday example of this is when you have a door and it has a damper on the top, like that one. But I already tried that one. That one doesn't work very well, okay? But you know, when you open a door that has a damper, if you're going to open it very quickly, sometimes it's hard to push it. But if you just let it move, or if you open it slowly, you do not fall into resistance of the damper. So the damper will have a higher resistance depending on the velocity of the door. That's why it closes very, very slowly. Can you tell me an example of rock failure in less than a second or in a few microseconds in petroleum engineering. Fractures are usually pretty fast, but I'm thinking about something really fast. Like where we could say that, oh, you know, we're loading a rock in the terms of microseconds.
Really?
Yes. Drilling could be getting to a high rate of failure, but there is one which is even faster, in which sometimes we have explosives. Perforations. With perforations, sometimes you load the rock very, very quickly. And loading the rock very quickly, it brings about some other properties of the rock. It's stiffer, it fails in different ways than it would fail very slowly. What would be an example of a very slow rock failure? Tectonic movement will be very slow, right? It will take thousands of years, if not millions of years. And after that, something that we can cause any example?
When big skyscrapers are constructed, it usually pushes the ground down a little bit.
That would take the loading in terms of several years, or if not more, like, you know, like the Leaning Tower of Pisa. That's an example of deformation taking place over 100 years. But what about in petroleum engineering? How can you cause loading in the terms of tens of decades? Reservoir depletion. Reservoir depletion usually takes several years, if not decades. And when we do reservoir depletion, actually we're loading the rock. We're increasing the effective stresses, and that increase of effective stress is a very, very slow process. So usually when you do reservoir depletion and you want to understand, for example, deformations above the reservoir and inside the reservoir, you want to do your test as slowly as possible, because it is not the same to do it slow as to do it fast. Okay, so this is one example. We're going to call this number one manifestation of viscoelasticity. Number two is something that also you know, and this is going to be number three, that you know very well, and probably you will remember. Let's take that same example and load it, but now we're going to put time over here. And I'm going to apply a stress that increases linearly up to some point, and then at some time I keep it constant. And together with that, I also measure what is the strain. And I measure that strain also as a function of time. Let's assume that the rock deforms linearly with stress up to this point over here. And if this rock is viscoelastic, what do you think is going to happen with strain after this time over here? Do you think it will stop deforming? It will come back? It will deform more? Think about those grains here in the top, right? They are subjected to stress. So they are, bearing that stress. But if you have very small micro fractures or micro failure, the strain very likely is going to continue to grow. So if this will be constant, the strain will continue till it reaches a plateau. How is that called? I know you know this. What type of strain is that? Probably you heard it, but no temperature here. This is called creep. Okay? You never heard about creep? So creep is a deformation that continues with time with the same magnitude of stress. There are some rocks that are creepier than others, okay? There are some that they do not creep at all. There are some others that are very creepy, okay? For example of creepy rocks are salt rocks. Salt rocks, they have a lot of creep. Then, following category, probably we could put here mudstones. They also have a lot of creep. And sands, especially unconsolidated sands, they also tend to have a lot of creep. What that means is that if you subject the rock under a given state of stress, say with a maximum stress higher than the minimum principal stress, the rock is not going to fail instantaneously, but it's going to deform with time and very slowly. Are you guys familiar with salt diapirs? Yes? No? More or less? Anyone? You guys are from, some of you around Houston, right? No? No one? You? Well, around Houston, there are many places where you have salt diapirs very close to the surface. So let's see what those salt diapirs are. Or a salt dome. Okay, that's what a salt dome is. That's a cartoon. Let's look at one real. I like this one. So that's a salt diapir. What is that? At some time, when the sea evaporated, it left a lot of salt, a thick layer of salt. And after you put sediments on top, the salt has a lower mass density than the rocks, and because it deforms a lot with time, the salt will eventually break through some point in the sedimentary layers of sand and clay and will go up with time. So this one, for example, is still rising. Rises very slowly, is failing in shear all the time, is creeping, and sometimes it may go to the surface or close to the surface. Are you guys familiar with the oil strategic reserves? So in the oil strategic reserves, they keep oil in many times in some of these salt diapirs. They make a cavern in that salt diapir in order to use it as a big container for oil whenever that one is needed. So this is a very good example of creep, rocks that fail with time. This is failing right now, but very slowly. If you were to drill a wellbore in these kind of rocks, you wouldn't leave it uncased for a long time, because otherwise the rock will just slowly fail and close the wellbore. And if you don't do it quickly, you may get stuck pipe, or if you leave it uncased, it's going to close after some time. Oh, that was the wrong bottom. So these are creep strains, okay? Let's wait a minute till we get the image back. What's going on over here? Let me try this. Okay, let's wait 5 seconds. If not, I'll do it on the board. So we talked about, we're talking about viscoelasticity. We said rocks, the stiffness depends on the velocity of loading. Second, rocks can creep. And the third phenomenon, which is also very important, is very similar to the one we did here, but with one modification. What about if I were now to load the rock with a prescribed strain, and I load it up to a given strain, and I keep that strain constant with time? This is an exam question, guys. What is going to happen at this point with stress? So I load it, you see, I get to that point, linear relationship so far, but I wanted to know what is going to happen after. If I also have a rock that exhibits creep, you think the stress is going to stay the same? Is it going to grow? Is it going to decrease? Why decrease? But why does it make sense?
The creep phenomenon.
But why? So what? What is going on with creep?
I mean, that it kind of shows that if stress is constant, the strain's going to increase. So if the strain is constant,
Yeah.
that the stress is slightly going down.
So, yeah, when you load the rock is under a lot of stress, and nobody likes stress, right? So, if the rock inside is failing at the micro scale, all of that energy is going just to be gone, and usually what you will have here is that stress is going to decrease with time. And it depends also on the properties of the rock, how fast that decrease. Sometimes it may take a long time, sometimes it may take a short time. But this one is going to decrease. And this is what is called a phenomenon of stress relaxation. So for example, if today you were to prop a hydraulic fracture, say with a width of 1 inch, and you create a lot of stress near the fracture, after some time, that stress, because of the viscoelasticity of the rock, will tend to decrease. Or if you have a very large tectonic strain, some plate movement that makes your subsurface to be very compressed, after a very long time, even though at the beginning you may have had a very large stress, after a long time that stress is going to be inside the rock. The formation is still going to be there, but inside the rock the stress is going to be dissipated over time. Yes, Mr. Awa.
Is that stress going to become constant, or is it going to hit zero?
It's going to tend to a sort of a plateau to whatever the rock is comfortable with. If you have a salt rock, that's going to tend to zero, because salts cannot resist any shear stress. Salt rocks do not like shear stress, and this is going to tend to zero. Okay, so these are 3 things that you guys should remember very well. And when you're dealing to real problems, probably those are going to be very important in order to solve accurately whatever problem you're dealing with in geomechanics. Very closely related to this topic, we also have in rock mechanics some other types of loadings which are not only strain and stress. So let me add a page over here. I'm going to call it 29B. And this one goes under the name of multiphysics problems. So by now we know very well that if we get a rock and we apply a stress, we're going to get a given shortening and which we can calculate as a strain, right? So stresses lead to strains, strain lead to stresses. But can you tell me about some other type of loadings or some type of inputs that I could apply to the rock so it deforms too? Which is not applying stress. I'm going to keep the stress constant. And I'm asking you to think about some other ways of changing its size, changing its deformation. There is one. I'm going to ask you for one of those that you know very well. Let me think of an example, everyday example of that. Okay, well, I cannot come up with a good example. But what happens with temperature? What happens if you get a solid and you subject it to a change in temperature? Let's say that I have a solid over here and I change the temperature, I increase the temperature 100 degrees. What is going to happen to this solid, which is also a rock?
Expand in all directions.
It's going to expand, right? And how is that phenomenon there? It's thermal dilation, right? It's thermal dilation, and the opposite, if you lower the temperature, the rock will tend to shrink. Temperature, it plays a big role in mechanics. What about if I told you that I have this piece of rock over here, so this will be a positive delta T. I'm increasing the temperature. Let's now do a similar exercise in which I have a rock which is glued to the sides, and I have here a constant stress, and now I lower the temperature. So let's do one at a time. Now this is not as simple as that one, okay? The rock cannot move in this direction. This is what we call before the one-dimensional strain condition. But usually we used before for developing compressive stresses. But now we're lowering the temperature, okay? And the rock cannot move in this direction.